Hello, my Math 130s. Today we're going to go over homework alternate chapter 8 and 9, intro into exponential functions, which will cover numbers 7 through 11 for this assignment. Essentially, let's go to our whiteboard here. Hopefully we won't have any issues with this. Let me pause. Okay, there we go. So I just went to a different screen here. So chapter 8, 9, homework alternate, intro to exponential functions. Okay, so a few details. First, the definition. An exponential function has the following form. You're going to have your function name. In this case, it's f of x. And then you're going to have a to the x power. Remember that a is your base and x is your exponent. So now we're looking at functions where the part that varies, the input, is going to be in an exponent spot. Okay, later we're going to look at the inverse functions for these, which will be called logarithmic functions. That will be in our next video. Okay, so a few details. Okay, if a is greater than 1, you're going to have what's called exponential growth. And you're going to have a graph that looks sort of like this, just looking at the shape right now. Okay, there's going to be this asymptote too that's worth mentioning. For an unshifted exponential graph, this line here would be y equals 0. Okay. In this case, your domain will be negative infinity to infinity. That's for your x values. Okay, and then your range, which will cover the y values, will be 0 to infinity. Okay, so we will approach 0 for the y values, but we'll never touch it. Okay, if a is less than, sorry, one more detail. If a is between 0 and 1, you have exponential decay. And your graph is going to look like this. You're going to have that asymptote again at y equals 0. And then essentially your domain is still going to be the same. And your range will also be the same. Okay. if a is equal to 0, you would have f of x equals 0 to the x power. Okay. And this would give you a constant function. With the exception of a weird spot. Okay. If x were equal to 0, this would be undefined, but you don't need to worry about that. Okay. And then if a is equal to 1, you would have 1 to the x power. Gives you a constant function. And this is true even if x is 0. So this would be a constant function. No discontinuities. So these are both not exponential graphs or functions. Okay. Also, you don't want to have negative a values. You're not going to get an exponential function. You're going to get one that alternates between negative and positive. Okay. So just really note these bounds that we're talking about for your base. Okay. Let's save a picture of this. And then we're going to actually talk about how to graph. So let me clear this out. And then let's go back to our note guide here. Okay, guess we're not going back to, there we go. Okay. All right, so the first question we're going to be looking at in order to talk about graphing these is going to be question 7. The function g is defined by the following rule. Let's write that big up here. G of x equals 9 to the x power. Find g of x for each x value in the table. So we have, we'll make the table, actually we won't make the table bigger. We'll just plug things in later here. So we have x values given. We want to find the function values at those corresponding x values. So let's start with x equals 2 first, because that one's more self-explanatory when we plug it in. We're saying, well, what is g evaluated at 2? That's going to be 9 evaluated at x equals 2, so 9 squared, which is 81. When x is equal to 1, g evaluated at 1 is equal to 1 squared. That's 1. X equals 0. G evaluated at 0 is 0 squared, which is 0. Sorry, what am I doing there? My bad. Bad me. So let's try that again. G of 1. Let's color code this a little bit so that I don't forget. 9 is your base. So that's the part you're taking the exponent to. So this fix here, g of 1 should be 9 to the first power. G equals 9. When x equals 0, evaluate g at 0. Remember, you have a base of 9 and a power of 0. And any number to the 0 power real number. Is equal to 1 with exception 0 to the 0 power, okay? So this is actually going to be 1. Okay. Let me clear out this side over here. Let's look at the negative exponents. For this part, you're going to want to review your exponential rules from chapter 4. When x is equal to -2, we have g of -2. That's going to be base 9 taken to the -2 power. Remember, that's going to be the same thing as 1 over 9 to the -2 power, which is the same as 9 over 1 squared. Ay. No. That was also my bad. Let's try that again too. Come on, Christine. Having one of those days today. So recall, this will help me out too to just write it out. So if we have a to the -x power, that's a over 1 to the -x power, which becomes 1 over a to the positive x power. And then that's going to be 1 to the x power divided by x to the a power, which is 1 over a to the x. So I think I just got tripped out with my color coding here. So we're actually going to make this into 9 over 1 first. I'm just going to leave it all in green. And then your power at that point is still -2. Next step, we're going to change the exponent to a positive. But when we do that, we need to switch the numerator and denominator of the fraction inside the base spot. Okay, that's 1 squared over 9 squared, which is 1 over 81. When x is equal to -1, g of -1 equals 9 to the -1 power. I'm just going to do this one a little faster, same color. That's 9 over 1 to the -1 power, which is 1 over 9 to the first power. Okay, so that's 1 over 9. Okay, you see a picture of that. So that's our first step. We don't have to graph this particular problem, but it's going to help us for graphing with the next problem. You do want to be familiar with your tables and being able to plug in and analyze expressions. Okay. Remember, this is an equation right here, right? But when we're trying to figure out what this expression is equal to, we have to simplify this expression on the right. Clear all that. Let's move to the next page. All right. This one, we're asked to graph the exponential function g of x equals 2/5 the quantity to the x power. So let's go ahead and establish our base here is 2 over 5. And our exponent, let's color code it a bit. Exponent will be x. Okay, let's make a table. So we'll use -2, -1, 0, 1, and 2. We'll do g of x in purple over here. When x is equal to +2, we'll start at the positive side. We have g of 2 that's going to equal the quantity 2/5 squared. Okay. That's going to be 2 squared over 5 squared, which is 4 over 25. Okay. Don't worry about the graphing of that yet. Just fill out your points first. Okay. When x is equal to 1, g of 1 is going to equal 2/5 the quantity to the first power. That's going to be 2 to the first over 5 to the first, which is 2/5. Remember, any number to a power of 1 is still itself, right? And then 2/5 to the 0 power, that's going to be 1. Save that. Let's plug in our negatives. When x is equal to -1, g of -1 is equal to the quantity 2/5 to the negative first power. So flip 5/2 to the first power, just 5/2. And then x is -2. I'm not going to color code this one. G of -2 is equal to the quantity 2/5 to the -2 power. That's 5/2 squared, which is 25 over 4. So there's this weird reciprocal thing that happens with exponential graphs and fractions for base. So 25 over 4. Okay, that's our first step. Now, if Alex actually allows you to plug in points, you can plug in these points as long as it allows you to do it with fractions. But in case not, you can use a calculator for this part just to make it a little bit faster. If you're trying to evaluate 25 over 4, come on. So 25 over 4, remember that's the same thing as 25 divide 4. Okay, so it'll be 6.25. Okay, so this first point that we have on our graph will be -2, 6.25. Okay, next one, -1, 5 divided by 2, that's going to be 2.5. You have the nice 0.01. You have 1 2/5. That's going to be 0.4. And then 4 over 25, that's going to be 0.16. So the last point is 0.16. Let me save a picture of this and let me try to zoom in a little here if this will allow me to. Oops, do not undo anything. There we go. I'm trying to do it all from the graphics tablet so that it's not messing up as much. Okay, so let's move this out the way. No. Okay, come on, really? There we go. It's hard because you have to find a straight line to attach on and move it. Otherwise, if you don't do it with a long enough straight line, it just starts moving your size adjustment. Okay. Same thing over here. Let's try to get one of these lines. Okay, yeah. Okay, there we go. All right, so let's graph these roughly. I'll try to curve them, but it's probably not going to come out looking the best. So we have -2, 6.25. So 6 is here, and then 0.25, that's a fourth. So we've got a fourth of the way up here. Okay, of course it wouldn't draw anything in there. Okay. And then you have -1, 2.5, 2.5 way. You have 0, 1, 1, 0.4. That's a little bit less than 0.5, which is half, so a little bit less than half. And then 2, 0.16. It's pretty small, so just guesstimate from there. Okay, so that's what it's going to look like. If you were to keep graphing points toward the left, they're going to be more stretched out and come up this way. Be pretty steep. And if you keep plotting points on the right here, they're just going to keep getting closer and closer and closer to the line y = 0, but it won't reach. So let's make a little line here. So this line right here is y = 0. It's actually a horizontal asymptote for your exponential function here. Okay, so I'd like to make that dotted, but I can't. All right, now I'm going to try to draw this in. It's, you know how this goes with the graphics tablet, so it might not look the best. Not at all. Something like that. Okay, you get the general shape, hopefully. Like imagine all this being completely smooth and going through all the points, okay? All right, so let me go ahead and clear this out. I'm gonna move to number 9 next. We're still working with exponential functions here. The dollar value v of t of a certain car model that is t years old is given by the following exponential function. Find the initial value of the car and the value after 11 years. Round your answers to the nearest dollar as necessary. So for this, I want to make a few points. We have this function v of t. Okay. And it's equal to this 24500 times 0.88, and it's to the t power. Let's add something in here. Okay, so this is our general function that we have here. So a few notes. We have our base for the exponential function, that's 0.88, which is also the same as 88/100ths. I want you to note that that's less than 1. Okay. So we would have one of those graphs that looks like this. This is called exponential decay. Okay. Next thing I want to note is that t is our input, and it's also our exponent. It's like normally where x would be, right? And then I want you to know that we have a coefficient out in front of those items of 2, 4, 5, 0, 0. This is going to just stretch or shrink our graph. Okay. And then our function value is going to be the v evaluated at whichever t we put in. Okay. And now I want to just put the general formula over here. For an exponential growth or decay problem. So you're going to have your v of t equaling p sub 0. That's how that's pronounced. Times 1 plus r to the t power. P sub 0 is that coefficient you're seeing. And that's essentially, actually, I don't want to use a p there. Let me get rid of this for right now. And then let me pause for one moment because I want to figure out exactly how I want to state this. All right, you guys, so I figured out how I want to state this. First, I'm going to just state it like not in function form. So this is going to be 2 variable form. It'll be a little bit easier to explain that way. So one is going to be exponential growth. Your formula for this will be y equals a times 1 plus r to the x, where r is positive. Okay. To color code this a bit, like for our when we get to function stuff, y is our function value. A is the coefficient. Your 1 plus r is the base. And x is the exponent. Okay. So let me put what these values are over here. Y is your function value. That's still going to apply when we put it in function form. A, your coefficient is your initial value. Which is essentially your y value when x is equal to 0. R is your growth rate. In decimal form. And then X is going to be the time passed. Okay, so let me go into decay first, since that's the type of example we have here. So for exponential decay, we're going to have something very similar, but with some mild differences. So y equals a times 1 plus r to the x power, but now r is negative. So it's a decay rate, okay? Similarly, y equals a times the quantity 1 plus r to the x power, okay? So y is still going to be your function value. A is still going to be your initial value, which is basically found by setting x equal to 0. And then your r for this decay rate in decimal form, specifically when r is less than 0. And x is still the time passed. You save a picture of this. So now we're going to have function form. Just to bring this back. Okay, so like in comparison, you might see something like v of t replaced for the function portion. You see that your coefficient is going to be noted v sub 0. Okay, what that means is you have your function v evaluated at time 0. Okay, and then you're going to have your rate 1 plus r. And then if you have a t right here, you're going to have a t up here. Okay, so this is like the form that we have right now. Now you might be thinking, how do we know if we have decay or growth without seeing the 1 plus r part? From here, like we discussed before, 0.88 is less than 1, but still greater than 0. So we're going to have decay. If we had a number greater than 1 here, we would have growth. Okay. All right, so that was kind of a lot to go over for that, but it's useful for what we need to talk about next. Clear out this whole bottom part here. Okay, so now we get back to question 9 in detail. Find the initial value of the car. Note that the dollar value is given as V of t. Okay. So this initial value you're looking for is going to be a y value. Okay. And then the value after 11 years, that's also going to be a y value. Just note that 11 years, that part's going to be your time. Okay, so let's look at, call this part A and part B. For part A, the initial value of the car, what you need to look for is the coefficient. And since it's a dollar value, you have dollars on it. Okay, so for initial value, look at the coefficient. Part B, you're looking for V of 11 years. It's the value of the car at 11 years. So V of 11 will be equal to your 24500 times 0.88 to the 11th power. Now, as long as you put parentheses and stuff in the right place, you can put all this into your calculator at once. If you do that, this comes out to 6004.481043 in your calculator. Now remember, you want to look for what you need to round to here, round to the nearest dollar. So that's about $6,004. Okay. If I would just suggest putting it in your calculator exactly like this. If you can't, though, for whatever reason, start with this part first and then multiply the coefficient out front. Okay, let me clear this out. We're going to move on to question 10 next. Okay, suppose that the future price P of T of a certain item is given by the following exponential function. In this function, P of T is measured in dollars, and T is the number of years from today. It's color-coded a little bit again. So we have our P of T, and that's going to equal your initial value times your 1 plus R, which in this case is 1.028. And then you're going to have your input time T. Okay, so find the initial price of the item. If you have P of T here, this would essentially be your P sub 0 coefficient. So it would be $2,500. Does the function represent growth or decay? So right here, we see that 1.028 is our base. That's greater than 1. So we're going to have growth in a graph. If we graphed it, that looks something like this. Okay. By what percent does the price change each year? Essentially, what that part comes from is your 1 plus R. By what percent? This is going to be your growth rate. Growth or decay in decay cases. Rate R. Okay. So your percentage is going to change by, so you have your rate of 0.28, okay, which means you have a 28% growth rate. So 28%. Okay, how do I know that? Just off to the side, I have 1.028. That's going to equal 1 plus R. So if I subtract 1 from both sides, I have 0.028 equals R. Oh, and then I just found, oops, another error. 1, 2. Okay, so our rate is actually 0.028, which means we have a 2.8% growth rate. Let me erase this. Okay, so this should be 2.8%. Okay, sorry about that. So yeah, I would actually recommend doing that just so that you don't mess that part up. Okay, let me save that, clear this out, and then we're on our last problem for this particular video. You can see we're going to get into logarithmics very shortly. Okay, so this next one, to begin a bacteria study, a petri dish had 2,900 bacteria cells. Each hour since, the number of cells has increased by 9.8%. Let T be the number of hours since the start of the study. Let Y be the number of bacteria cells. Write an exponential function showing the relationship between Y and T. So for this part, one second here. Okay. Let's color code some things. So to begin a bacteria study, we have 2,900 bacteria cells. So that means our coefficient, which is our initial value, is going to be 2,900. Each hour since, the number of cells has increased by 9.8%. So our growth rate, because of the increase, will be 9.8%. Okay. Remember, you can take 9.8 and just divide it by 100 if you're not sure about the bouncing your decimal. But essentially, you're just going to bounce your decimal 2 spots to the left. So you get 0.098. That's going to be R. Next, T is the number of hours since the start of the study. That's going to be your input, which is the exponent. and then y is going to be your function. Now, I kind of don't like how Alex puts this. They say write an exponential function, and then in their answer, they're going to give you a function just as y. That's technically a two-variable form, not a function form. If you wanted to make it a function form, it'd need to be y of t, but don't worry about it. Just make sure that you put it the way Alex wants you to put it, okay? All right, and then remember the form that we're matching to here. Let's put our general form. We're going to have, in this case, y equals a, it's 1 plus r to the t power. Okay, so that's what we're going to need. So let's just fill this in over here so we don't have to erase anything. Y is going to equal, your A value is 2,900. You're going to have 1 plus the decimal form of R, which is 0.098. And you're going to have that to the t power. Alex will probably want you to fully simplify this, which is what you should typically do anyway. So y will be 2,900 times 1.098 to the t power. Okay, so that would be enough for this particular problem. Again, I just want to make emphasis that this is really a two-variable form. It's fine though, because you can still think it's still going to be a function, okay? But technically in function form, you'd have y of t equals 2,900 times 1.098 to the t power. Okay. All right, that concludes this particular video. I will post this up later this evening, and then we'll go from there.